How do you tell one bathroom full of statisticians from another? You check the p-value. And yes, we'll be checking the p-value as we look at the model for sampling distributions for the differences of the means. So the main difference, no joke intended, no pun intended, is we have this delta naught represents the difference between the means of our populations for our hypothesis, all right? This is usually going to be 0. We're usually assuming there's no difference between the means. Then our standard error is just like before. We're using the Pythagorean theorem of statistics because we have 2 samples. And so we'll have the standard deviation squared plus the standard deviation squared, take the square root. For our test statistic, instead of having a z-value, we have a t-value. So we take the difference between our 2 samples minus our hypothesized value, which is usually 0, and divide by our ruler for statistics, which is our standard error, since we don't know standard deviation. All right? Okay, so to pool or not to pool. So when you're doing your t-test, you're going to find out that you can either do pooled or not pooled. Remember when we did it in proportions, we said, oh, okay, we're assuming that the 2 proportions for the 2 samples are the same, which means I can recombine them to find out my new proportion. And when I do that, I can actually calculate a standard deviation for the proportion pooled, all right? For means, that's not the case because we'd have to assume the variances are equal for this to work. But there's no link between mean and standard deviation. So that's not really a good reason to pool. There are some rare instances where the variances are the same and you do pool, and this would be called a pool t-test. It might be appropriate if I was doing an experiment, so I took one group and started from the same population and randomly assigned them. And then in that case, I can assume that the variances are the same because I'm starting from the same population. Don't do it unless you're sure. It is never wrong not to pool, but it can be wrong to pool for means. So it's better just not to do it. So let's go ahead and perform some t-tests. So we're going to revisit our example with smokers and their pulse rates. And my null is going to be that there is no difference between pulse rates for smokers and non-smokers, that the difference is equal. I'm also going to, for my alternate, I'm going to say, oh, smokers is higher than non-smokers. All right, so one-tailed upper test. And if we look at the conditions here, it's the same as before. I'm looking at the same example from our confidence intervals. Random is given. Independence is pretty reasonable for this sample. The nearly normal condition, they told us that the data is roughly symmetric and there are no outliers, so we meet those conditions. Let's go ahead and do the mechanics. So we still have the same numbers as before. Let's go ahead and we still calculate the standard error as we did before. Now, instead of doing a t-value from a table, I'm calculating the t-value, the test statistic, from the formula. 80 minus 74, so that's 6 minus 0, divided by 1.44 is 4.15. All right. I can't really go much further without my calculator, so let's go ahead and pull it up. And with this, I can go ahead and calculate my p-value and my degrees of freedom. I actually don't know my degrees of freedom. So you go to stats and you put in your values, 80, 5, 26, 74, 6, and 32. And we're assuming that smoking is higher than non-smoking. That's our alternate. That's not really our assumption. That's our alternate. And if I hit draw, you can probably guess my probability is very low because a t-value of 4.15, that's going to be kind of out there. All right, so you can see a very low probability. Sometimes it's better, instead of doing the draw, especially if you have the low p-values, is just do the calculate. So if you hit calculate, the nice part is you'll see your degrees of freedom right up here, 56. And it also has the p-value, which is that very small number right there. Okay? Now our conclusion. Because the p-value is so small, the observed difference is unlikely to be just sampling error. We reject the null hypothesis. We have strong evidence of a difference in mean pulse rate for smokers and non-smokers. In our next example, we're looking at fat content in 2 pizza chains like we did before with our confidence interval, except now we're doing a hypothesis test. So my null is that the difference is 0, that they're the same. And right now I'm just going to do a two-tailed. I'm going to say that my alternate is that they're not different. Okay. So here are the saturated fat content. So we're looking at the conditions. Independence, the 2 samples were chosen independently of each other. There's no mention that these were randomly selected. So we're going to say we will assume that they're representative. If we can get representative in there, that kind of covers us. Nearly normal conditions, since we have the histograms here, both distributions are roughly unimodal and symmetric. So make sure you have a histogram to double check that. All right, so the mechanics. Here are our values for our n and our mean and our standard deviation for both groups. Calculate the standard error like we did before. And now we can calculate the t-statistic, the test statistic right here. So we've got that minus 0 all over our standard error. And so from our calculator, let's go ahead and do that. We can find the degrees of freedom. So it's supposed to be 32.757 and a very low p-value. So if we go to SAMP t-test, now I'm doing data. So I just need to make sure I have the right list. And I'm doing doesn't equal mu, not mu of 2. And if you hit calculate, you can see the values up there. There's the 32 and there's the p-value. And you can also graph it. But because it's such a low p-value, it's going to be kind of boring. It'll be pretty much an empty normal distribution. And with a p-value of roughly 0. So there you go. Again, not as much benefit to drawing. I think the drawing's more helpful when you have the higher p-value. Okay, so our conclusion here is since the p-value is very low, we reject the null hypothesis. There is strong evidence to suggest that the 2 pizza brands have different mean saturated fat content. Brand D appears to have more saturated fat on average than brand PJ. Notice the word appears. If they had said brand D has more saturated fat on average than brand PJ, you would get dinged because you're saying something definitive. And we're usually not definite about anything in statistics. All right, one last add-on that's not really on your AP test, but it's kind of cool. This is called Tukey's quick test. So it works when you have one group that's really high and one group that's really low, and you're pretty sure they're different anyways. Count how many values in the high group are higher than all the values in the lower group. Add the number of values in the lower group that are lower than all the values in the higher group, and you count ties as a half. If this total is 7 or more, we can reject the null hypothesis of equal means at alpha equals 0.05. So the critical values of 10 and 13 also give us alphas of 0.01 and 0.001. All right, and it's just, you can probably really just use it as a quick check of your t-test. So if we revisit our pizza, here are all, the highest value for brand PJ was 11, so I circled everything higher than 11. The lowest value for brand D was 5, so I circled everything lower than 5. Then I circled the ties. Maybe I shouldn't count these 11s, but I'm going to count them anyways. All right. So I've got 6 higher, 4 lower, plus 6 tied. So I'm getting 13, or basically a p-value of 0.001, which kind of jives with what we were doing with before. So again, I would never report this p-value. I would treat it more as let's do a quick check. Okay? So this is not on your AP test. All right, what can go wrong? Watch out for paired data. So if you were looking at where you do a before and after treatment, that does not work with differences of means. Look at the plots. You got to check for outliers and non-normal distributions. Remember, you need at a minute, ideally it'd be normal when you have the low end value. Otherwise, at least unimodal and symmetric is what we're looking